Hello student. Today I'm going to discuss from this book, your textbook Calculus with Applications, Chapter 6, Section 3, which is about elasticity of demand, which is a part of the application problem that we already discussed. Let the function q equals to f of p to be under consideration. Q is the demand function at a price p. Therefore, E equals to minus p divided by q times dq over dp can be defined for elasticity. In short, I can write it down as a capital E for elasticity. It stands for elasticity. Capital E stands for elasticity. There are three cases, actually. If E is smaller than 1, then what we have is called the demand is inelastic. If E is greater than 1, the demand is elastic. The third case, which is the most important one, is when E is equal to 1, therefore the demand has the unit elasticity. In other words, from letting the E be equal to 1, we can find the price, actually, the P, small p. So this is the starting point. To make things a little more in a simplified form, I give you an example of elasticity from your own book. And example 4 I have, which is very nice example. And question is this: for this example, actually, example 4, the demand for beer was modeled by Hogarty and Elizinga with the function given by Q equals to f of p, which is equal to 1 over p. So these are function actually. Q is equal to 1 over p. Questions can be discussed. The three conditions, above conditions that I just put it here as a definition. The formula was E equals to minus p over q times dq over dp as the elasticity. Let's discuss actually the three cases. We have to start actually from the definition which is related to the revenue. Actually, the revenue is nothing but the product of P and Q. You have the quantity, you have the price of each quantity, therefore the Q times P or P times Q, it will give you R, which is equal to QP or PQ. And now this is a PQ. If we take the derivative of this with respect to P, then of course it is not difficult to see that we could use the definition of a product rule. The formula for the product rule is telling you if this is U, this is V, therefore U times V. You could use the formula for the product rule, which is called U prime times V plus V prime times U, and that will give you the derivative of R with respect to P. So derivative of R with respect to P actually would be, by definition here, the derivative of P with respect to P is equal to 1 times Q. So it would be Q plus. Then what you have is a derivative of this, dQ over dP times P, dQ over dP times P. So this is what we have run so far. And then, of course, if we can write this in this form, like multiplied by Q and then divided by Q. I tell you why we are doing this later on. Therefore, dr over dp is equal to Q times P over Q, dQ over dP, plus Q. So nothing happens here, just this Q and this Q will be cancelled. You'll get exactly the same thing we had over here. It's just right now you can see that this is nothing but the definition of E above if you put a negative, if you multiply by a negative. In other words, if E is the negative of this, therefore this, the product is equal to negative E if you multiply by negative. So that would be negative E plus Q. That's what we have. So far we have equals to Q times negative E plus Q, which in fact is nothing but if you take the Q out as a common factor, it becomes negative E plus 1. And this is the point that we are interested. Or you could write it down this way, just switch 1 and negative E, bring the 1 first because it's positive perhaps, and minus E. And then here, the three cases will be a start. Three cases that we have is either E is smaller than 1, then this becomes positive, or E is bigger than 1, this parenthesis become negative, or Q is equal to 1, this becomes 0. 1 minus 1 is 0. 0 times Q becomes 0. Therefore, so there are three cases actually for dr over dp, which in fact, the first one will give you positive, the second case will give you negative, the third case will give you 0. And that means actually r prime, the derivative of r with respect to p, is nothing but positive means you're going up, negative means you're coming down, and then equal to 0, you will have maximum. So there are three different situations here. And the first case, when that is a positive, that means the case that we have it is E smaller than 1. And therefore, the demand is called inelastic. So the first part is from here to here, is inelastic. Demand is inelastic. The second case is when r prime is less than 0, which means your function would be decreasing. The derivative is, the function is negative. The derivative is negative, therefore the function is decreasing. And therefore, what you have is actually the case number 2, which we had it, and that case was the demand is elastic. And the third case, of course, it leads you to the point which we have a maximum because it's the critical number you can find. To find the critical, you have to take the derivative of your function with respect to the variable that you have here. We assume that p is our variable, small p as a price. Therefore, if that's equal to 0, that will give you unit elasticity. Remember here we have three cases, case 1, case 2, case 3. Therefore, this is the general definition. Again, I have another example which will be a lot better maybe to understand it in terms of numerical. Numerical means I give you some numbers. For instance, here, example 5 is good. I can give you example 5. And example 5 is nothing but assuming that the demand for a product is this. Q is equal to 216 minus 2p squared. So you have a demand in terms of price. Q is the demand function to have a 216 minus 2p squared, where p is the price in dollars. Where p is the price in dollars. All right? Okay. Part A, the question they're asking you. Can you find the price interval where the demand is elastic? Demand is elastic where demand is inelastic. So there are two cases that we had, case 1 and case 2. They're asking you, can you solve it? Yes. First, we take our function, take the derivative with respect to p of both sides. Here would be dq divided by dp. Derivative of 216 is equal to 0. Derivative of negative 2p squared. Because derivative of p squared is equal to 2p times negative 2 becomes negative 4p only. So it becomes 0 minus 4p. And this is dq over dp. Now if you go back to the definition, the formula that we had for elasticity, and the formula was actually E is equal to minus P divided by Q times dq divided by dp. So now I have dp divided by dq is equal to minus 4p, this minus 4p. So I have this minus 4p. And on the other hand, also I have if you look at the formula, I have minus P divided by Q. So I have minus P. I can write it down here, minus P divided by dP. That one can write it down. You take this, which is a Q. Q actually is equal to, Q is given to you, 216 minus 2P squared. And then times dQ over dP. dQ over dP is minus 4P. Therefore, what you have, this is your elasticity. This elasticity, if you look at it, which negative times negative becomes positive, and then 4P times P would be 4P squared divided by 216 minus 2P squared. Then you go by three cases. Definition is actually this. Then you want this to be equal to 1, starting from here, from the third one, the unit elasticity. The third case of the definition was unit elasticity. When E is equal to 1, the demand is a unit elasticity. So unit elasticity means E must be equal to 1. And try to do this equation, solve it. Solve for P and find P. How do we do it? We multiply both sides by 216 minus 2P squared. In other words, you do cross multiplying. That's what you do. Cross multiplying, they will give to you this equation. 4P squared equals to 216 minus 2P squared. And if you bring everything one side in terms of P squared, you will get P squared, and 4P squared and 2P squared would be 6P squared. That's equal to 216. You divide both sides by 6. Therefore, P squared becomes 36. And this is telling you that P is equal to 6. Negative is not acceptable. Therefore, now you have a choice that to discuss. You could assume anything smaller than 6, or you could assume anything bigger than 6. Let's assume P equal to 1, something smaller than 6, like 5, 4, 3, 2, and 1. Perhaps 1 is the best one, dealing with the numbers, positive numbers. So it will be 4 divided by 216 minus 2. When you substitute in E, you get 4 over 214. Whatever this one is smaller than 1. So we say E is smaller than 1. Remember that? That E is smaller than 1. This is what the definition is. When E is smaller than 1, the demand is inelastic. So in this case, when we say like P is equal to 1, therefore E becomes smaller than 1, which means inelastic. Demand is inelastic. If it's 2, it's the same way. If it's 3, it's the same way. 4, same way. As long as it is smaller than 6, same way. You will get capital E is smaller than 1. Therefore, the demand is inelastic. Now, let's, the second case, try anything bigger than 6, like 7, 8, 9, 10. Perhaps here, 10, they assumed. For simplicity, 10 squared is simple. We can do it like 100 times, so it's 400. Then 216 minus here would be, again, 200. So you subtract this, you will get this 400 divided by 16. That would be a number bigger than 1. So that's just a first case. The second case, that's the first case, inelastic. This is elastic. So we say in this case, when P is anything bigger than 6, like 10, therefore E becomes bigger than 1. So our problem in this situation, the demand is called elastic. So we answer to those questions. When is inelastic, when is elastic? That's the part A was. Then, of course, there is a part B also, is a continuation of that they're asking you, can you find the total revenue, which is it is maximized. Total revenue is maximized at price where the demand has unit elasticity. So if we substitute 6, not something bigger than 6, not something smaller than 6, the 6 by itself, in Q, therefore Q becomes 144. So when P is equal to 6, Q becomes 144. In other words, the P times Q, which is equal to R, the maximum revenue becomes P times Q. Remember, R was P times Q. So we are using R equals to P times Q. That's R equals to P times Q. And that's a maximum revenue. They give you maximum. And again, to see that why do we have maximum, if you take the second derivative, that becomes less than second derivative is concavity, and then concavity down, that means you have maximum. Concavity down, you will have maximum. Concavity up, you will have minimum. So this is the solution to this example, and we use actually these two examples just to explain what is elasticity of demand. That's all for today. Have a nice day. I will see you here again